Hi all, welcome to Go Classes. In this lecture, we are going to solve previous year questions of GATE exam, TIFR exam based on these topics of graph theory, vertex cover, matching, independent set, clique. Let me tell you, in this lecture, for each GATE and TIFR PYQ, we are going to do the complete analysis. Also, to solve any question, the concepts that are required, we will do the recap of those concepts also. So this session is basically self-sufficient. In this lecture, first I will do the recap of the concepts. To solve any question, what concepts we need, we will do the recap, and then we will solve the question with complete analysis, with variations, with proof, everything. Okay. So let's start this session. Take your copy pen. Let's solve all these questions together. Don't watch it like a movie. Let's solve all the questions together, you and me. Okay. Let me tell you, you can find all the discrete mathematics, Go classes, discrete mathematics, all the lectures, all the GATE PYQs lectures, all the compact lectures, compact course, practice questions, revision playlist. So you can find on the YouTube. On YouTube, you can search discrete mathematics Go classes, and this playlist will be there. In this playlist, you can find all the discrete mathematics, GATE PYQs, compact lectures, practice questions, and so on. Okay. Let's quickly do the recap of the definitions of these concepts: vertex cover, clique, independent set, matching, edge cover. So let's do the quick recap. Let me tell you, these concepts, clique, independent set, and vertex cover, these concepts, these are set of vertices concepts, and edge cover comma matching, these concepts, these are set of edges concepts. Okay. So let's see the definition. What is a clique? Clique is a set of vertices which are pairwise adjacent. Means every two vertices are adjacent. What is independent set? This is set of vertices which are pairwise non-adjacent. Means every two vertices are non-adjacent. What is vertex cover? This is set of vertices which will cover all the edges. Now, what are the definitions of edge cover matching? These are set of edges concepts. So edge cover, this is set of edges which will cover all the vertices. Remember, vertex cover, this is set of vertices which will cover all edges, and edge cover, this is set of edges which will cover all the vertices. I told you that vertices will cover edges, edges will cover vertices. So vertex cover means set of vertices which will cover, which will touch all the edges, and edge cover means this is set of edges which will cover, which will touch all the vertices. What is matching? Matching is edge independent set. Means this is set of edges which are pairwise non-adjacent. See the difference between independent set and matching. Independent set, this is set of vertices which are pairwise non-adjacent, and matching, this is set of edges which are pairwise non-adjacent. Means every two edges are non-adjacent. What is non-adjacent edges? Two edges are non-adjacent if they do not share any common vertex. Okay, they do not have any common endpoint, they do not share any common vertex. Very simple. So these are the definitions of these concepts. Now let me tell you, to solve all the GATE PYQs, to solve all the TIFR PYQs, and to find the proof of any theorem, any result, any concept, we just need to apply these definitions. On your screen right now, what is written, this is enough to solve all the questions. Okay. So let's quickly see this table. You can see set of vertices concepts and set of edges concepts. Vertex cover, this is set of vertices concept. This is set of vertices which will cover all the edges. And remember, there is a corresponding concept for edges, that is edge cover. This is set of edges which will cover all the vertices. Similarly, for vertices, we have a concept independent set, that is pairwise non-adjacent vertices. Now there is a corresponding concept for edges also, that is matching, that is pairwise non-adjacent edges. Okay, so you can see these concepts, these are corresponding concepts for vertices and edges. What is clique? Clique is basically set of pairwise adjacent vertices, set of vertices which are pairwise adjacent. Means this clique, this is basically a complete subgraph Km, because in a complete graph Kn, every two vertices are adjacent. And what is the definition of clique? This is set of pairwise adjacent vertices, means every two vertices are adjacent. So this is basically a complete subgraph in the graph G. If you have a graph G, in this graph G, what is a clique? Clique is basically a set of pairwise adjacent vertices, or I can say this is a complete subgraph. So remember, this is your graph G. In this graph G, a complete subgraph is a clique. Okay, very simple. So for example, you can see this is a clique because this is a complete subgraph K3. You can see this is a clique because this is complete subgraph K4, and every edge is a clique because this is complete subgraph K2. Every vertex is a clique because it is complete subgraph K1. Okay, very simple. So I hope you understood. And remember, this clique, this is set of vertices concept, and there is no corresponding concept in the edges. Okay, so this clique, this does not have a corresponding concept for the edges. We have a clique. This is basically pairwise adjacent vertices, or I can say complete subgraph in the whole graph, in the entire graph G. A complete subgraph is called clique. Very simple. Now we have some numbers associated with these concepts. We have clique number. Clique number means size of maximum clique, size of largest clique in the graph. That is called clique number. So this clique number, this is of course integer because this is size of largest clique, and this is denoted by omega. Okay, we denote by omega of G. What is independence number? This is size of largest independent set in the graph G, size of maximum independent set. So this independence number, this is denoted by alpha of G. Vertex cover number, this is size of smallest vertex cover in the graph G, size of minimum vertex cover. And what is the symbol for, what is the notation for vertex cover number? That is beta of G. What is edge cover number? Edge cover number means size of smallest edge cover in the graph G, size of minimum edge cover, and the symbol is, the notation is beta dash of G, because these are corresponding concepts for edges comma vertices, right? So for vertex cover number we have beta G, this notation, and for edge cover number we have beta dash G, this notation. Okay, what about matching number? Matching number means size of maximum matching, size of largest matching in the graph G. And what is the notation? The notation is, you can use mu G you can use, or you can use alpha dash G. Why alpha dash G? Because I told you, independence number, matching number, these are corresponding concepts for vertices comma edges. Independence number is for vertices, matching number is for edges. Okay, what is independent set? Independent set, this is set of vertices which are pairwise non-adjacent. And what is matching? Matching is set of edges which are pairwise non-adjacent. Okay, so that's the reason this alpha G, alpha dash G, these are the notations for independence number and matching number respectively. Very simple. I hope you understood. Now let's solve some questions based on the definitions of these concepts: vertex cover, clique, independent set, matching edge cover. Based on the definitions of these concepts, there are some UGC NET questions, and there are some more interesting questions that I have taken from the standard resources. So let's solve. Let's solve UGC NET June 2013 question. A vertex cover of an undirected graph G, V, E is a subset of vertices. It's a subset V1 of vertices such that, basically the question is asking the definition of vertex cover in a graph, in an undirected graph. What is the definition of vertex cover? This is what the question is asking. So what is the definition of vertex cover? Vertex cover, this is set of vertices which will cover all the edges of the graph. Very simple. So vertex cover of an undirected graph, this is set of vertices that will touch all the edges of the graph. So what I can say, if we are covering all the edges, if we are touching all the edges, then what it means? It means that for every edge, at least one endpoint belongs to the vertex cover. Yes or no? Because remember, the responsibility of vertex cover, that is to touch all the edges, to cover all the edges of the graph, right? Okay, so let me write it here. You can see you have G, V, E. This is the graph. What is vertex cover of G? Let's assume that is S. Okay, so vertex cover of G, what is the responsibility of vertex cover? If you say that this S, this S is subset of V. If you say that this S is a vertex cover, what it means? It means that it should cover all the edges. Means every edge should be covered by this vertex cover. Okay, so let's assume that this S is a vertex cover. Then it simply means that this this vertex cover, this S, this is S. Okay, now this vertex cover will cover all the edges. It will touch all the edges. It simply means that the edges will be like this, or maybe the edges will be like this. Yes or no? Where are the edges? The edges will be like this, the edges will be like this. The point is, this vertex cover S will touch, it will cover all the edges. So remember, we cannot have this type of edge which is not covered by this vertex cover, because vertex cover, the definition says that it is a set of vertices that will cover all the edges, that will touch all the edges of the graph. So if I am saying that this S is vertex cover, it simply means it will touch all the edges of the graph, it will cover all the edges of the graph. So remember, this type of edge is not possible which is not covered by this vertex cover. Okay, this type of edge is not possible. Agree? So what I can say? I can say that every edge will have at least one endpoint in this vertex cover. Okay, at least one endpoint in this vertex cover. Every edge will have at least one endpoint in this vertex cover. Very simple. I hope you understood. Both are also fine. For example, this edge has both the endpoints in this vertex cover. This edge has both the endpoints in this vertex cover. This edge has one endpoint in this vertex cover. But the point is, this vertex cover should cover all the edges. So every edge, whatever edge you take, that will have at least one endpoint in this vertex cover. Okay, so this is the definition. A vertex cover in the graph is a set of vertices such that every edge will incident, every edge is incident on at least one of the vertices of this vertex cover. Okay, in simple words, I can say that a subset of vertices S, this S is subset of vertices. A subset of vertices S is vertex cover if and only if for each edge at least one of its endpoints will be in S. Okay, this is the definition of vertex cover. I hope you understood. Very simple. Okay, so what will be the answer for this UGC NET June 2013 question? A vertex cover of undirected graph GVE, it is a subset of vertices, that is fine, such that what should happen? For every edge, it should happen that at least one of its endpoints must be in this vertex cover. Okay, so I can actually write it that, let's assume we have a graph G, V, comma E. Okay, and we have this S. Let's assume this S is subset of V. Okay, now remember, S is vertex cover. S is vertex cover of G if and only if for all edges what should happen? If and only if for all edges E, what should happen? If E is a edge between two vertices U comma V, okay, if this is a edge whose endpoints are U comma V, then I can say that at least one of these endpoints must be present in S. Yes or no? Because for all the edges, at least one of their endpoints must be present in the vertex cover. Okay, so you can see that for all the edges, I can say that if E is U comma V, means it is between U comma V are the endpoints, then I can say that either U belongs to S or V belongs to S. Okay, or both, no problem. Okay, or both. So very simple. I hope you understood. So the answer will be that this V1 is a vertex cover. V1 is subset of V. Vertex cover is subset of vertices. So this V1 is vertex cover. Then what will happen? For every edge, if U comma V, if there is a edge between U comma V, then U belongs to V1 and V belongs to V1. No, at least one of them must be present in the vertex cover. Yes or no? So the answer will be option C. I hope you understood. Very simple. Okay, you can see if there is a age between u comma v, then either u must be in v1 or v must be in v1 or both. That's fine. Okay, so basically by default this or contains both also. Okay, we already know when we say p or q, what this means. What this means when we say p or q, it simply means p or q or both. Okay, so I hope you understood. Very simple. Now what about the remaining options? This v1, this is subset of vertices. What about the remaining options? What about option a? What does it define? Option A is saying every pair of vertices in v1 is connected by an edge. Means this v1 is subset of vertices, and option A is saying that every two vertices of v1 are adjacent. So this is the definition of clique. Yes or no? Option A defines clique. Option A defines that v1 is clique. Yes or no? V1 is a clique. I hope you understood. But the question is asking for definition of vertex cover. Okay, option A is defining clique. What about option B? What about option B? In option B, what will be V1? Can anyone tell me? Think about it. Pause the video, think about it. In option B, we are saying that if there is a edge between u comma v, then both the vertices, both the endpoints of this edge belong to v1. Okay, means for every edge we are saying whatever edge you take, both the endpoints of that edge will belong to v1. Then what will happen? In this case, what will happen? In this case, I can say if this graph is, let's assume, connected, then definitely this v1 will be equal to v. Yes or no? V1 will be equal to v if G connected. Okay, if G connected and the number of vertices is greater than equal to 2. Okay, I hope you understood this point. Very simple, right? Because option B is saying that whatever edge you take, both its endpoints will belong to v1. So if your graph is connected and we have at least two vertices, then definitely this v1 will become v. Okay, this v1 will become same as the set of vertices. Okay, so definitely it does not define the vertex cover. Okay, option C is correct, that we already have seen. What about option D? All the pair of vertices in v1, they are not connected by an edge. Means in this v1, every two vertices are non-adjacent. So option D actually defines what? This actually defines that v1 is a independent set. Okay, because what is independent set? This is set of vertices, or I can say this is subset of vertices which are pairwise non-adjacent. So option D is defining independent set, option A is defining clique, option C is defining vertex cover, option B does not define basically anything. Okay, so this is the complete analysis of this UGC NET question. I hope you understood. Let's solve UGC NET December 2019 question. A clique in an undirected graph. We have undirected graph G, V, comma E. Then what is a clique? The question is asking for the definition of clique. We already know that clique is basically subset of vertices. So yes, V dash, this is subset of V. So V dash is basically subset of vertices. Now the question is asking what is the definition of clique? We already know clique basically means this is subset of vertices which are pairwise adjacent. It means if this V dash, if this is a clique, then between every two vertices of V dash there is a edge. Every pair of vertices of V dash, they are connected by an edge. Okay, so very simple this definition. What is clique? Clique is basically a set of pairwise adjacent vertices, means every two vertices are adjacent. Or I can say that clique is basically a complete subgraph Km, a subgraph which is complete. Okay, what is clique number? This is the size of largest clique, and this is denoted by omega g. Okay, or I can say that what is clique number? Clique number means size of largest clique, and size of largest clique means in the graph G, what is the largest complete subgraph? That size of largest complete subgraph, that will be clique number. Okay, but we already know that the definition of clique, we already know that if you have a graph G, if you have a graph G, V, comma E, and let's assume that S is subset of V, then when can I say that S is clique? We will say that S is clique if and only if between every two vertices of S, for all vertices that belong to S, for all U comma V that belong to S. Okay, means every two vertices that belong to S, what should happen? There should be edge between them. Means UV, they should belong to the edge set of the graph. Okay, very simple. I hope you understood that they should be adjacent. Okay, this is the idea. Very simple. Here, this simply means U comma V are adjacent. Okay. So what will be the answer here? A clique is basically a subset of vertices such that every pair of vertices in VDS is connected by an edge. Okay. So the answer will be option C. What about the remaining options? Let's see the option A. If UV belongs to E, means basically if there is a edge between U comma V, then both of them belong to VDS. Again, this option basically is saying that whatever edge you have, both the endpoints they belong to V dash. Okay, then here you can see if your graph is connected and you have at least two vertices, then definitely V dash will be same as V. Yes or no? So here you can see that this V dash will be same as V if G connected. If G connected and we have at least two vertices in the graph. Very simple. Okay. So option A is basically nonsense option. What about option B? It is saying that if there is a edge between U comma V, then at least one of them belong to V dash. Either U belong to V dash or V belong to V dash or both. Okay. So at least one of them belongs to V dash. So that will be the definition of vertex cover. Yes or no? This option B, this actually defines vertex cover. Okay. And you can see option C that defines the clique. And what about option D? All pairs of vertices in VDS are not connected by an edge. So this option D, this defines independent set. This defines independent set. Okay, that's it. Very simple. I hope you understood. Tell me the answer for this question. Which of the following statements? Which of the following statements defines a vertex cover in graph G? Four options are given: at least one vertex per edge, at most one vertex per edge, at least one edge per vertex, at most one edge per vertex. Pause the video and solve this question. Try this question. This is little bit confusing, but just remember the definition of vertex cover and you can solve it. So what is the definition of vertex cover? This is subset of vertices which will cover all the edges. Yes or no? So we already know that vertex cover is basically a subset of vertices. You can see vertex cover of any undirected graph, that is a set of vertices, or I can say a subset of vertices that will cover all the edges of the graph. So I can say a subset of vertices S is subset of vertices. A subset of vertices S is vertex cover if and only if for each edge at least one of its endpoints must be in S. Yes or no? Okay, very simple. That vertex cover, what it simply means, it will cover all the edges. It will touch all the edges. Okay, vertex cover, this is set of vertices. Okay, this is I can say set of vertices that will touch all the edges. So if we have a vertex cover, let's assume this S is vertex cover. Okay, this is S, where S is subset of V, and this S is vertex cover. Then what it means? It means that if this S is vertex cover, then definitely this vertex cover will cover all the edges. It will touch all the edges. Okay, it will touch all the edges. Very simple. Every edge will be covered by this vertex cover. Okay, whatever edge you take, that will be touched by this vertex cover. So remember, this type of edge we cannot have. this type of edge whose both endpoints are out of this S. Okay, this type of edge is not possible. Why this edge is not possible? Because we are saying that S is vertex cover, so it means it is touching, it is covering all the edges. So you can see if you have this type of edge whose both the endpoints are out of S, then definitely this edge is not covered by this S. So S is not a vertex cover, but we are saying that S is vertex cover. Okay, very simple. So I hope you understood that the definition of vertex cover, it is basically a subset of vertices such that for every edge I can say at least one of its endpoints will belong to S, will be present in S. Okay, so I can say which of the following statements will define vertex cover? I can say at least one vertex per edge. Yes or no? Remember, vertex cover is set of vertices, or I can say it is basically subset of vertices. Okay, vertex cover, it is basically set of vertices. So these options, these two options are gone. These two options are gone because these two options are set of edges. Option C comma D, these are basically set of edges. Correct? But remember, vertex cover is set of vertices. Okay, so here these two options are gone because option C is saying at least one edge per vertex, at most one edge per vertex. But remember, vertex cover is set of vertices. Okay, so the correct answer will be at least one vertex per edge. Yes or no? Yes, that is correct. So this is the correct answer, that in the vertex cover there will be at least one vertex per edge. For every edge, at least one of its endpoints will belong to the vertex cover. I hope this point is clear. In the vertex cover, we will have at least one vertex per edge. Okay, this is the idea. So answer will be option A. Tell me the answer for this question. Which of the following statements is the definition of edge cover? At least one vertex per edge, at most one vertex per edge, at least one edge per vertex, at most one edge per vertex. Which of the following options will define edge cover? We already know the definition of edge cover. Edge cover means set of edges that will cover all the vertices. Okay, edge cover means this is subset of edges, or I can say set of edges that will touch, that will cover all the vertices of the graph. So I can say that this edge cover, this is basically a subset of edges. A subset of edges S is subset of edges. This will be edge cover if and only if for every vertex at least one of the edges that incident on it must be present in S. Very simple point. See, whatever vertex you take, okay, whatever vertex V you take, let me take this vertex V. Now, if these are the edges that are incident on V, then definitely to cover this vertex V, we must take at least one of these edges in the edge cover, because edge cover means this is subset of edges that will touch, that will cover all the vertices. So if I want to cover this vertex V, then look at these edges, at least one of them must be present in the edge cover. Yes or no? At least one of these edges, at least one of these edges must be present, at least one of these edges must be present in edge cover. Okay, yes or no? In edge cover. I hope you understood this. Very simple point. Remember, this vertex V and these are the edges that are incident on V. We want edge cover. Edge cover means set of edges that will touch, that will cover all the vertices. So to cover this vertex V in the edge cover, we must take at least one of these edges. Okay, so you can see that for each vertex we must take at least one edge that is incident on this vertex in the edge cover. Okay, very simple. I hope you understood this. So what will be the answer here? That edge cover, this is set of edges that you already know. Okay, edge cover is basically set of edges. This is not set of vertices, this is set of edges. So option A comma B are gone, because option A comma B, these are basically set of vertices. You can see at least one vertex per edge, at most one vertex per edge. So option A comma B, these are basically set of vertices. So these two options are gone. And what is edge cover? edge cover, it touches all vertices. Okay, so whatever vertex I take, okay, means for all vertices, I can say for any vertex, for all vertices, remember, for all vertices A that belong to V. So what should happen? For all vertices, this should happen that this is A and these are the edges that are incident on A. Then remember, at least one of these edges must be present in any edge cover. Okay, at least one of these edges must be in any edge cover, in every edge cover, in edge cover. Very simple. Okay, so I can say the definition of edge cover means at least one edge per vertex. Okay, yes, at least one edge per vertex. For every vertex, I can say that at least one edge incident on this vertex must belong to edge cover. So at least one edge per vertex must belong to edge cover. So the answer will be option C. Very simple. Tell me the answer for this question. Which of the following statements define independent set of a graph? These four options, they are confusing, but if you just think about the definition of independent set, then you can easily solve it. What is independent set? It is set of vertices which are pairwise non-adjacent. So you can see a set of vertices which are pairwise non-adjacent, that is independent set. So remember, in the independent set, what should happen? If there is a edge, just consider this edge, any edge you can consider, whatever edge you consider this edge E, and let's assume these are the endpoints A comma B. Then what can you say? Then one thing is certain, that both of these A comma B cannot belong to independent set. Yes or no? Okay, I can say that at most one of A comma B, at most one of A comma B must be in independent set. Independent set. Yes or no? Do you agree with me that at most one of them will be in independent set? Because we are talking about independent set, means set of vertices which are pairwise non-adjacent. So in the independent set, we cannot put both these vertices A comma B because they are adjacent. Okay, so remember, this is the definition, that a subset of vertices S is independent set if and only if for every edge we can say that at most one of its endpoints will belong to independent set. Okay, remember, it can happen that maybe none of them belong to independent set, that is fine, but the point is it should not happen that both of these A comma B belong to the independent set, because A comma B are adjacent. So I can say that at most one of them will be present in the independent set. Okay, and this will happen for every edge. I can say that independent set simply means at most one vertex per edge. You are taking at most one vertex per edge. You cannot take both the vertices per edge. Okay, you will take at most one vertex per edge. Okay, so you can see the answer, at most one vertex per edge. This will be the answer. Okay, I hope you understood, because whatever edge you take in the independent set, you can see for all edges, E, if this edge E has endpoints A comma B, okay, if this is the situation, then I can say that at most one of A comma B will be in independent set. Okay, that's it. Very simple. I hope you understood. So I can say that independent set simply means in the independent set, we have at most one vertex per edge. Per edge, at most one vertex. We cannot take both the vertices of any edge. So at most one vertex per edge. Tell me the answer for this question. Which of the following statements is the definition of matching? Again, the four options might be confusing, but remember, just apply the definition of matching. What is matching? This is set of edges which are pairwise non-adjacent. Okay, so you can see matching of undirected graph. It is set of edges which are pairwise non-adjacent. So what it actually means, if you have a vertex V, consider a vertex A. Let's assume this is the vertex A, and these are the edges that are incident on A. Now you tell me, in the matching, can you take more than one edge that is incident on A? Tell me. Very simple question I am asking, that this is your vertex A, and these are the edges that are incident on A. So in any matching, whatever matching you are creating, in any matching, can you take more than one edge that incident on A? Can I take, for example, these two edges in matching? The answer is no, because remember, all these edges that are incident on this vertex A, all these edges are adjacent, and matching is set of edges which are pairwise non-adjacent. In the matching, we have non-adjacent edges, but remember, all these edges which are incident on this vertex A, these are adjacent because they are having a common vertex. This A is the common vertex for all these edges. This A is the common vertex, so all these edges that are incident on this vertex A, these are adjacent edges. So I can say that at most one of these edges will be present in any matching. Yes or no? So here I can say that, here remember, I can say these edges, look at these edges. Okay, so I can say that at most one of them, at most one of these edges will be in any matching. Okay, I hope you understood, because all these edges, these are adjacent edges, because they all are incident on this vertex A, so they are all sharing this common vertex A, so these are actually adjacent edges, and matching is non-adjacent edges. Okay, so I can say that in any matching, at most one of these edges will be present in any matching. So what I can say, that in any matching, at most one edge per vertex we are taking. Notice, per vertex, at most one edge we are taking, at most one edge that is incident on this vertex we are taking in the matching. So you can see, a subset of edges S is matching if and only if for each vertex at most one edge that is incident on it will be present in the matching. Okay, very simple. I hope you understood. So per vertex, at most one edge we are taking in the matching. So the answer will be at most one edge per vertex. Okay, this is the definition of matching. I hope you understood. Okay, very simple. So overall, did you notice all these statements? Look at these statements. This is the conclusion. This is the conclusion. These statements, what they define, you can see, at least one vertex per edge. Per edge, we are taking at least one vertex. This is your vertex cover. Yes or no? This is your vertex cover. Per edge, at least one vertex we are taking. So this is vertex cover. We have already seen. At most one vertex per edge we are taking. Okay. Per edge, at most one vertex we are taking. So this is independent set. This is independent set. Next, at least one edge per vertex we are taking. Per vertex, at least one edge we are taking. So this is edge cover. We have already seen. And what about the last? At most one edge we are taking per vertex. Per vertex, at most one edge we are taking. So this is matching. Okay, that's it. Did you find this question beautiful? In the gate exam, if they ask you this question, let's assume they give you in column 1, they give you these terms. In another column, they give you this, and they ask you to match the columns. Okay, this is your column 1, this is your column 2, and the question asks you to match the columns. Then I guarantee you one thing. Okay, most of the students will make mistake, because these are confusing statements, at least one vertex per edge, at most one vertex per edge, at least one edge per vertex, at most one edge per vertex. So these are actually confusing. These statements are confusing. So definitely many students, they will make mistake in this question if this question comes in the gate exam, where in one column you have these terms and in another column you have these terms. But did you understand? Please tell me. We have already seen the explanation of each of them. Did you understand? Let me know. Is it crystal clear? So you can see, I found this in a top university. So you can see, this question is actually taken from a top university slides. Okay, you can see here. Matching means at most one edge per vertex. Edge cover means at least one edge per vertex. Vertex cover means at least one vertex per edge. Independent set means at most one vertex per edge. You can see these are edges concepts and these are vertices concepts. Okay, very simple. Tell me the answer for this question. This is what I was talking about just now. I told you that in one column you have these concepts and in another column you have these properties. Then the question can ask you to match the columns. So what will be the answer here? Notice one thing, that look at matching. Matching, this is a edges concept, right? This you already know that this is edges concept. This is set of edges which are pairwise non-adjacent. So this is edges concepts. So definitely you can remove this and you can remove this. Okay, because these are vertices. See, here we are talking about vertices, at least one vertex you are taking, at most one vertex you are taking. But matching means edges concepts. You need to take edges. Yes or no? Okay, so you can see that these two options are gone. Now, in the remaining two options, you are taking edges. So matching means non-adjacent edges. So you can easily see that non-adjacent edges means per vertex, how many edges you will take. See, per vertex, because both these options are saying that, okay, per vertex, how many edges we will take in the matching. So you can see, if you have per vertex, if you see, this is your vertex A, then per vertex, at most one of these edges we will take. Yes or no? Do you agree? At most one is, at most one is per vertex. Okay, very simple. So the answer here will be at most one is per vertex. So remember, P will match with 2. Okay, P will match with 2. So these options are gone. I hope you understood. Similarly, you can see, what about edge cover? This is also edges concept. Okay, this is also edges concept, set of edges. So again, you can remove this, because this is talking about, this is taking at least one vertex, this is taking at most one vertex. Basically, these are, this 1,3, they are taking vertices. But edge cover means this is the edges concept. Okay, now you can see, in the remaining these two statements, we are talking about per vertex. Okay, so tell me, per vertex, what will happen in the edge cover? Per vertex means you take a vertex. Per vertex, what will happen? Edge cover means we want to cover all the vertices. We want to cover this vertex A. To cover this vertex A, at least one of these edges I will take. Yes or no? At least one edge per vertex I will take. Okay, do you agree? So here you can see at least one edge per vertex. So Q will match with 4. Q will match with 4. Okay, very simple. And similarly, you can see the remaining two. You can see vertex cover. This is vertices concept. Vertex cover. This is a vertex concept. Set of vertices, basically. Okay, so this is a vertex concept. It simply means these two options are gone because they are taking edges. Okay, at most one edge, at least one edge, but they are taking edges. But vertex cover is set of vertices. Okay, now you see, per edge what will happen. Okay, remember, in the remaining two statements, these are the remaining two statements. In the remaining two statements, the question is saying per edge what will happen. Okay, so let's consider per edge. Let's assume this is the edge E. Okay, per edge what will happen? Vertex A, vertex B. So tell me, vertex cover means we want to cover all the edges. I want to cover this edge E. So A or B, at least one of them I need to take. Do you agree with me? Okay, so I can say that to cover this as E, to cover this as E, I can say that at least one vertex per edge I need to take. One vertex per edge I need to take. Okay, at least one of these I need to take. I hope you understood. Very simple. So I can say at least one vertex per edge I need to take. So R will be matching with 1. Okay. And what about the independent set? Independent set, this is vertices concept. This is a vertices concept. This is set of vertices. Okay, so you can remove this 2 comma 4 because they are edges. Okay, they are taking edges. So tell me, independent set. In the remaining two statements, you can see we are talking about per edge. Okay, per edge, what will happen? So consider any edge. Okay, per edge, let's see what will happen. This is A, this is B. Now, independent set means this is set of vertices which are pairwise non-adjacent. So I cannot take both A comma B in the independent set because A comma B are adjacent. Yes or no? So you can see per edge, at most one vertex I will put in the independent set. Yes or no? Okay, so you can see at most one vertex per edge I will put in the independent set, in any independent set. So I can say S will match with this independent set will match with at most one vertex per edge. Okay, so this is, so the final answer you can easily see. The final answer will be matching means at most one edge per vertex. Okay, P2. So you can see P2. Okay, so these options are gone. Next, you can see edge cover means at least one edge per vertex. Okay, so you can see Q4. Okay, Q4. So this is also gone. You can see Q4. So this is also gone. And of course, you can see vertex cover. This means at least one vertex per edge. Okay, so this is correct. And you can see independent set means at most one vertex per edge. At most one vertex per edge. Okay, so finally the answer will be option A. That's it. I hope you understood this question. Let me tell you, in the GATE exam, this question might feel tricky. Okay, these statements and these concepts, because these are confusing statements. So in the GATE exam, this type of question might feel little bit tricky. But all you have to do, just apply the definition. Okay, I hope you understood these questions that we have seen. Okay. Now let's see some GATE TIFR UGC NET questions based on relationship between vertex cover, clique and independent set. In the previous lectures, in our conceptual lectures, we have already seen relationships between these various concepts. With proof we have seen. Now these are the GATE and TIFR questions which are based on these concepts, basically relationships between various concepts. You can see this is GATE CS 2005 question. It is asking about the relationship between independent set and vertex cover. This is TIFR 2016 question. It is asking for the relationship between vertex cover and independent set. This question is based on relationship between vertex cover and independent set. You can see this TIFR 2024 question. It is based on relationship among vertex cover, independent set and clique. Okay, among all these three concepts, the relationship based on that is this question, TIFR 2024 question. So these three questions let's solve, and all these three questions, these are based on relationships among these concepts, vertex cover, clique and independent set. Okay, let's quickly do the recap of relationship between vertex cover and independent set. What is the relationship? Let's quickly see the recap. The proof, the concept, everything we have seen in our lectures, in our previous lectures. You can find the link in the description, in the pinned comment. So let me tell you the relationship between vertex cover and independent set. If S is independent set in the graph G, then the remaining vertices will be vertex cover in the graph G. We are talking about graph G. In the graph G, if a subset of vertices S, if that is independent set, then the remaining vertices will make vertex cover. Similarly, if S, which is subset of vertices, if S is vertex cover, then the remaining vertices v minus s, that will be independent set. Okay, so I can say that S is vertex cover in the graph G if and only if the remaining vertices are independent set in the graph G. Or I can say that S is independent set in the graph G if and only if the remaining vertices v minus s is vertex cover in the graph G. So you can see these two concepts, vertex cover, independent set, these two concepts are basically complementary in the graph G itself. Okay, these are complementary in the graph G itself. Means if S is independent set, then the remaining vertices is vertex cover. If S is vertex cover, then the remaining vertices is independent set. So these two concepts, vertex cover comma independent set, these two concepts are complementary in the graph G itself. Okay, so let me make the diagram, because using diagram, using visualization, it will be easy to remember. So you can see what we are saying. We are saying that this is the graph G. This is the graph GVE. Okay, and in this graph GVE, you can see, let's assume this is S. Okay, this is S, and so basically these vertices, this is S, and the remaining vertices, that will be V minus S. So we are saying that if this S is vertex cover, we are saying if this S is vertex cover, if this S is vertex cover, then the remaining vertices will become independent set. Okay, the remaining vertices, that is independent set. Similarly, this is your graph G V, same graph. Okay, so in this graph, if S, if this S, which is set of vertices, subset of vertices, and this is V minus S, these are the remaining vertices. So you can see if S is independent set, if S is independent set, then what will be V minus S? This will be V minus S will be vertex cover. Okay, I hope you understood. Very simple. So you can see if S is independent set, then the remaining vertices V minus S will be vertex cover. If S is vertex cover, then the remaining vertices V minus S, that is independent set. So we can say that S is vertex cover if and only if the remaining vertices is independent set. We can also say that S is independent set if and only if the remaining vertices V minus S will be vertex cover. Okay, so these two concepts are complementary in the graph G itself. I hope you understood. Now let's see some more concepts. All these concepts with proof we have seen in the previous lectures. Okay, you can find the link in the description in the pinned comment. So let's see some more points here. You can see these 2 points we have already seen, that if S is vertex cover, then the remaining vertices is independent set. If S is independent set, then the remaining vertices is vertex cover in the graph G. Now similarly, remember, if S is minimum vertex cover in the graph G, we are talking about graph G. So if S is minimum vertex cover, then the remaining vertices will be maximum independent set. Means if S is smallest vertex cover, then the remaining vertices will make largest independent set. If S is largest independent set, then the remaining vertices V minus S, they will make smallest vertex cover. Similarly, if S is minimal vertex cover, then the remaining vertices, they will make maximal independent set. If S is maximal independent set, then the remaining vertices V minus S, they will make minimal vertex cover. Okay, very simple. I hope you understood all these points. So let me again just quickly make the diagram. So you can see S is minimum vertex cover of G if and only if the remaining vertices, that is maximum independent set of G. Okay, so I can say if this is the graph G, GV comma E, if this is the graph G, and let's assume this S, this is set of vertices, and this V minus S, this is the remaining vertices. So here, if this S is minimum vertex cover, if this is smallest vertex cover, if this is smallest vertex cover, then the remaining vertices, that will be largest independent set. Okay, then that will be maximum independent set. Okay, I hope you understood. And similarly, of course, you can say that, similarly, I can say this is the graph GVE. Similarly, I can say that if this S, set of vertices, and these are the remaining vertices. So if this S is a maximum independent set, if this is maximum independent set, then the remaining vertices, that will be smallest vertex cover. Okay, then the remaining vertices, that will be minimum vertex cover. Okay, I hope you understood. This is what this statement means, that if S is minimum vertex cover, smallest vertex cover, then the remaining vertices will make largest independent set. If S is largest independent set, then the remaining vertices will make smallest vertex cover. Okay, very simple. Similarly, if S is maximal independent set, then the remaining vertices will make minimal vertex cover. Okay, just let me quickly make this diagram. From this diagram you can understand that this is the graph GVE. Here, if this S is subset of vertices, these are the remaining vertices, V minus S. Then here we are saying, if this S is a maximal independent set, if this is maximal independent set, then the remaining vertices, V minus S, that will be minimal vertex cover. Okay, that's it. So all these points we have already seen in the previous lecture also. You can find the link in the description, also in the pinned comment. But let's see quickly the proof. Okay, so there is a cute proof. Whatever we have seen, basically the relationship between vertex cover and independent set, that we have seen, there is a cute proof for that. Let's quickly see this cute proof. We have already seen in the previous lecture. You can find the link in the pinned comment in the description. But let's quickly see this cute proof. So remember, in this cute proof, we are going to just apply the definition, nothing else. We will apply the definition of vertex cover. We will apply the definition of independent set. Okay, so let me share with you this cute proof. You can see we have a graph GVE. Okay, so let's assume this is the graph GVE. This is the graph. In this graph, let's assume that this S, this is the set of vertices, subset of vertices. This is S, and of course, these are the remaining vertices, V minus S. Okay, so a very simple question I'm asking you, that if this S is independent set, let's assume this S is independent set. Let's assume this is given to you. Let's assume this is given to you, that S is independent set. Then can you tell me what will be V minus S? What this V minus S will be? Very simple question, that in the graph G, V, E, this is subset of vertices S, and that is independent set. This is given to you. So what will be the remaining vertices? What that will be? Just apply the definition. Let me give you a hint. This is the hint. Where are the edges? If this subset of vertices, if this is independent set, then where are the edges? The edges cannot be in this area. Okay, we cannot have this type of edge, because this area, or I can say this set of vertices, this subset of vertices, this is independent set. So these are pairwise non-adjacent. So there is no edge in this area, I can say like this, because these are pairwise non-adjacent. So where are the edges? Where are all the edges? There is no edge in this area. So where are all the edges? All the edges will be maybe in this area. Edges can be in this area, or maybe like this, one endpoint here, one endpoint here, like this. Okay, yes or no? I hope you understood. Where are all the edges? But remember, there cannot be any edge in this area, because these are pairwise non-adjacent. Okay, so this type of edge, I can say that this type of edge is not possible, because these are pairwise non-adjacent. This S is independent set. Okay, so you can see this type of edge is not possible. So finally, I can say that what is this V minus S? Means this area, these vertices, that is vertex cover, because it is covering all the edges. You can see this area, this subset of vertices, this is touching all the edges. This area, V minus S, this is touching all the edges, this is covering all the edges. So what is V minus S? This is basically vertex cover. Okay, this is basically vertex cover. That's it. So what we have proven? We have proven that If S is independent set, then the remaining vertices will be vertex cover. Okay, very simple. This is what we have proven, that if S, if this S is independent set in the graph GVE, if this S is independent set, then the remaining vertices V minus S, these remaining vertices, that will be vertex cover. Okay, this is what we have proven. Very cute proof. Just using the definition of independent set, using the definition of vertex cover. Now, similarly, you tell me another question I am asking. Let's assume this is the graph GVE, and this is the subset of vertices S, and these are the remaining vertices. Okay, and let's assume this is given to you, that this S is vertex cover. Okay, this is vertex cover. This is given, this is already given to you, that this is vertex cover. Then tell me what will be V minus S. Very simple question. Again, let me give you the hint. The hint is, where are the edges? You just see where are the edges. Notice this S means this subset of vertices. This is vertex cover. What it means? It means this will touch all the edges. This will touch all the edges. These vertices, they will touch all the edges. Yes or no? This subset of vertices, this area S, this is vertex cover, means this will touch all the edges. Means every edge will be touched by this area S. Okay, every edge. Where are all the edges? The edges will be covered by this S. The edges will be like this. Okay, can you have this type of edge? For example, can you have this edge which is not touched, which is not covered by this S? Can you have this type of edge? This type of edge is not possible. Why? What is the reason? Because if you have this type of edge, now here you can see this edge is not covered by this S, but S is vertex cover, so it must cover all the edges. So if you have this type of edge, then S is not a vertex cover, but we are saying that S is vertex cover. It simply means this type of edge is not possible. So what I can say, if this S is vertex cover, then it is touching all the edges. It is touching all the edges. It is covering all the edges. Then what can I say about this remaining vertices, this V minus S? This is a pairwise non-adjacent vertices. Yes or no? Because look at these vertices in the V minus S. Any two vertices you take, they are pairwise non-adjacent. Okay, any two vertices you take, they are non-adjacent, because I cannot have any edge between them. Okay, yes or no? This type of edge is not possible. So you can see that this V minus S, this is subset of vertices which are pairwise non-adjacent. So this V minus S, this is basically independent set. Okay, that's it. I hope you understood. So what we have seen that if S is vertex cover, then V minus S is independent set. Okay, this is the graph G, VE, and if this S, if this is vertex cover, if this is vertex cover, then the remaining vertices V minus S, that will be independent set. Okay, very simple. I hope you understood. Very simple. These are the cute proofs. Okay, so this is what we have seen. I hope you understood that if S is independent set in the graph G, then the remaining vertices V minus S is vertex cover in the graph G. If S is vertex cover in the graph G, then the remaining vertices V minus S is independent set in the graph G. So I can say that S is vertex cover of graph G if and only if the remaining vertices V minus S is independent set of graph G. So these two concepts, vertex cover, independent set, these two concepts, these are complementary in the graph G itself. Okay, very simple. One more thing, this is actually important. So you can see, we have already seen that if S is minimum vertex cover, then the remaining vertices V minus S will be maximum independent set. Okay, so we have already seen this. If this is the graph GVE, this is graph GVE, okay, and this is the subset of vertices, and these are the remaining vertices. Okay, so you can see, let's assume that this S is a minimum vertex cover. Okay, this is a minimum vertex cover. So we already know that these remaining vertices, that will be maximum independent set. Maximum independent set. Okay. Now you already know the size of minimum vertex cover, that is called vertex cover number. Yes or no? So you can see the size of S, that is denoted by beta. Okay, because that is your vertex cover number. That is the vertex cover number. That is the size of smallest vertex cover. So you can see this S is minimum vertex cover. So the size of S, that is your beta. And what is this V minus S? This is the largest independent set. So the size of V minus S, the size of largest independent set, that is denoted by alpha, that is your independence number. That is the independence number. Okay. And you can see what is size of V minus S. Size of V minus S, that is basically size of V minus size of S. Or I can say that it is basically N minus size of S. So overall, what is the conclusion? Overall, what is the conclusion? Here you can see that alpha is basically N minus size of S. Size of S is beta. So I can say alpha is equal to N minus beta. So here I can say that alpha plus beta is equal to N. What is N? This is the number of vertices. Okay. And this is the equation. This is the important equation. I hope you understood this equation. Okay. The proof, with proof we have seen this equation. This is important equation. Okay. Is this clear? Let me know this equation. So remember, what is alpha here? This is the independence number, means this is the size of largest independent set. Size of largest independent set is called independence number, and this is denoted by alpha. And size of smallest vertex cover, that is called vertex cover number, denoted by beta. And this is the proof we have seen that alpha plus beta is equal to number of vertices in the graph. Okay, very simple. So all these concepts that are written in these slides, you can read these slides, everything we have already seen. Okay, independence number is also called stability number, because independent set is also called stable set. Okay, independent set, another name is stable set. So independence number is also called stability number. Basically everything that is written in these slides, in these screenshots, that we have already seen. We have seen that alpha plus beta is equal to number of vertices in the graph. Okay, let's solve gate 2005 question now. We have already done the recap of all the concepts required to solve this question. So what will be the answer? Let G be a simple graph with 20 vertices, 100 edges. The size of minimum vertex cover of G is 8. The size of maximum independent set of G will be what? Remember, we have seen, with proof we have seen that what is this size of minimum vertex cover? First of all, you tell me. Size of minimum vertex cover of G. This is called vertex cover number. This is called vertex cover number. Vertex cover number means size of smallest vertex cover in the graph G. So this is vertex cover number, and this vertex cover number is denoted by beta. Vertex cover number is denoted by beta. So beta is vertex cover number, that is the size of minimum vertex cover, size of smallest vertex cover, and this is given to you, that is 8. Okay, the question is asking the size of maximum independent set. First of all, you tell me what is size of maximum independent set. Size of largest independent set, that is called independence number. That is called independence number, and that is denoted by alpha. This is what question is asking. We have already seen that for any graph, alpha plus beta is equal to number of vertices. Okay, what is number of vertices? That is 20. Beta is given to you, that is 8. And alpha, the question is asking. So what will be alpha? Alpha will be equal to 12. Okay, so here for this question, the answer will be option A. Because remember, for every graph G, for any undirected graph G, we know that alpha plus beta is equal to number of vertices. The proof we have just now we have seen. Okay, just before this question we have seen the proof. So all the concepts required to solve this question we have already seen with proof. Okay, so here you can see alpha plus beta is equal to number of vertices in the graph. Number of vertices, that is 20. So here the answer will be alpha equal to 12. So remember, for this question, this number of edges, this is the useless information. This information, number of edges is 100. This is useless. Okay, because alpha plus beta is equal to number of vertices. Beta is given to you 8. So number of vertices is 20. So alpha will be 12. Very simple. I hope you understood. Let's solve TIFR 2016 question. To solve this question, all the concepts that are required, we have already seen. We have already done the recap of all the concepts required to solve this question. So let's solve this question now. A vertex cover in any undirected graph is a subset of vertices such that every edge has at least one endpoint in this vertex cover. An independent set in a graph is a subset of vertices such that no edge has both its endpoints in the independent set. Which of the following is true for every graph G and every vertex cover C of G? The question is asking which of the following is true for every graph G, whatever graph you take, and for every vertex cover. We have already seen that if C is a vertex cover in the graph G, if C is a vertex cover, then the remaining vertices will make independent set. Yes or no? So you can see whatever vertex cover C you take in any graph G, then the remaining vertices they will make independent set. We have already seen that independent set and vertex cover, these are complementary concepts within the graph G itself. So if you have C that is vertex cover, then the remaining vertices they will make independent set. So tell me which of the following statement is always true for every graph and for every vertex cover. So you can see if C is vertex cover, then the remaining vertices, what is remaining vertices? That is VG minus C. So the remaining vertices will be independent set. Yes, option B is correct. Okay, so for this question, the answer will be option B. We will do the complete analysis. We will see the remaining options also, why they are false. But did you understand that option B is correct? Okay, so very simple. Option B is basically correct because you already know this. We have already seen that in any graph G, this is the graph G. In any graph G, if you have subset S of vertices, and let's assume that this S is vertex cover. Here they are using the C. Okay, they are saying that C is vertex cover. Okay, so C, this is subset of vertices, and they are saying that C is a vertex cover. C is a vertex cover. So we already know that in any graph, if C, which is subset of vertices, if this C is vertex cover, then the remaining vertices, that means V minus C. Okay, the remaining vertices that will make independent set. Okay, so this will be an independent set. Okay, is this clear? With proof, we have already seen this in this lecture already. You can watch it. So finally, I can say that this is guaranteed that the remaining vertices V minus C that will be an independent set. Now let's see the remaining options. Why the remaining options are false? Can we find the counterexample for the remaining options? Remember, you must do the complete analysis of every question. Getting the answer is not enough. You should do the complete analysis of all the options. Basically, why the remaining options are false? Can you find the counterexample for all the remaining options? This will be interesting. So let's see. What about option A? Option A is false, but what is the counterexample? See, the question is asking which of the following statement is true for every graph G and every vertex cover C. Okay, so option A is saying that there exists an independent set of size C. So remember, this C is any vertex cover. It can be minimal vertex cover, it can be minimum vertex cover, it can be smallest vertex cover, it can be any vertex cover. Okay, may not be minimum, may not be minimal, it can be any vertex cover. Now The question is asking which of the following statement is true for every graph and every vertex cover, and option A is saying that there exists an independent set of size C. Is it necessary? Let me give you a counter example for option A. So what will be the counter example for option A? You can consider a complete graph. Consider K4. Consider K4. Okay. A, B, C, D. Consider this K4. This is the counter example for option A. In this K4, you can see we have vertex cover. Okay, let me give you a vertex cover C. C is vertex cover. Let me give you a vertex cover C. So, for example, vertex cover means set of vertices which will cover all the edges. In the complete graph, if I want to cover all the edges, then I must take at least n minus 1 vertices. Yes or no? Here we have 4 vertices. I must take at least 3 vertices. Any 3 vertices I can take in this complete graph. In the complete graph, to cover all the edges, the vertex cover must contain at least n minus 1 vertices. Okay, so you can see, for example, you can see ABC, this is a vertex cover. What about the independent set? In this complete graph, every 2 vertices are adjacent. Yes or no? In the K4, in the complete graph, every 2 vertices are adjacent. So tell me, what is the largest independent set you can create? You can see the independent set. The largest independent set that you can create, that will have a single vertex. Yes or no? If you see the maximum independent set that you can create, that will have a single vertex. For example, yes, this is a independent set. For example, this is an independent set. You cannot take 2 vertices, because if you take 2 vertices, they will be adjacent. So the maximum, the largest independent set that you can create, that will have a single vertex. Okay, yes or no? That will have a single vertex. So I can say that in this K4, there is no independent set of size 3. Yes or no? There is no independent set of size 3. But you can see this vertex cover has size 3. Here you can see the size of C, that is 3. But you can see there is no independent set of size 3 here. Okay, yes or no? So I can say that option A, that is false. If you have vertex cover C, then can I guarantee that there will exist independent set of size C? This is false. Okay, yes or no? And the counter example for option A, we have already seen this K4 count. This is the counter example. Okay, let's see the counter example for option C, D, E. So let me tell you that option C, D, E, these are also false. And the counter example for all of them, what you can do, you can use a star graph. Okay, see what option C is saying. Option C is saying that size of, first of all, you can see in the question, C is given to you in the question. In the question, what was C? C was a vertex cover. C was a vertex cover. Okay, now let's see option C, option C, option D, and option E. Let's see them. So in the option C, we are saying that the size of C will be greater than equal to number of edges divided by 2. Okay, size of C will be greater than equal to number of edges divided by 2. And you can see the option D is saying size of C is greater than equal to number of vertices divided by 2. Size of C is greater than equal to number of vertices divided by 2. And option E is saying that C intersects every independent set. C intersects every independent set. Okay, so let's see the counter example. Actually, for option C, for option D, for option E, for all of them, you can use the same counter example, that is a star graph you can use. Okay, what to do, you consider this star graph. Consider this star graph. Okay, here you have A, B, C, D, E. Okay, so you can clearly see in this star graph, this is star graph. Okay, this is star graph k1 comma 4. Okay, you can see k1 comma 4. This is star graph, or you can say that this is complete bipartite graph, where in one part you have A, in another part you have B, C, D, E. Okay, so you can see this is your star graph. Okay, clear? So now you can see here in this star graph, you can notice. Can you give me a vertex cover? Can you give me a vertex cover? Can you give me a vertex cover? A vertex cover C, can you give me? Yes, you can just take this A, this will be a vertex cover. If I take only this vertex A, then this will cover all the edges. So yes, this vertex cover is there. Now you can see what is the number of edges. Number of edges is 4. Here the size of vertex cover, that is 1. Okay, so you can see option C, this is gone, because you can see the size of C, that is actually 1. Is 1 greater than equal to number of edges divided by 2? Number of edges 4 divided by 2, that is 2. So no. Okay, so you can see option C is gone. What about option D? In option D also you can see the size of C, that is 1. Is this greater than equal to number of vertices, that is 5? 5 divided by 2, that is 2.5. Again, this is no. Next you can see, what about option E? C intersects every independent set. In this star graph, can you see there is an independent set, that is B, C, D, E? Yes or no? You can take these vertices B, C, D, E. That will be an independent set. Okay, so in this star graph, I can write an independent set here. I can write an independent set that will be B, C, D, E. Okay, so here you can easily see that this C, this vertex cover C, does not intersect with this independent set B, C, D, E. Yes or no? This is your vertex cover. It contains the vertex A. And you can see this is your independent set B, C, D, E. And they do not intersect. Yes or no? So I can say that option E is also gone. So finally, I can say that the counterexample for option C, D, E, the counterexample, let me write it here. The counterexample will be a star graph. Okay, you can just take a star graph, you can take that will be the counterexample for option C, D, E. This star graph you can take. Okay, and for option A, the counterexample you can take. You can take the counterexample like K4. Okay, will K3 work as the counterexample? Like if I take a K3, if I take K3, will it work as a counterexample? So you can see in the K3, the vertex cover size will be 2. Okay, at least 2 vertices we need in the vertex cover. And the independent set, there is no independent set of size 2. So here actually K3 will work. Okay, K3 will also work. You can see because in the K3 there is no independent set of size 2. Okay, but remember in the K3, the vertex cover size is actually greater than equal to 2. Okay, the size of vertex cover is actually greater than equal to 2. Whatever vertex cover you take, that will have size at least 2. Okay, at least 2 vertices you need to take in the vertex cover. Okay, correct. So remember in the K3, the size of any vertex cover will be greater than equal to 2, and there is no independent set of size 2. Okay, so finally I can say that the counterexample can be K3 or K4. I hope you understood. This is the complete analysis of this question. You can see, you can read. This is the comment I made on the Gate Overflow website under this TIFR question. This is my comment. Here you can see the counterexample for option A, that is complete graph K4 or K3 you can take. And the counterexample for option C, D, E, that is star graph K14. Okay. And option B is correct. So this is the complete analysis of this question. I hope you understood. Let's solve TIFR 2024 question based on relationship between vertex cover, independent set, and clique. So among these three concepts, vertex cover, independent set, and clique, among these three concepts, there is relationship, and based on that relationship, this question is based on that. Okay, so this is actually a very beautiful question. To solve this question, you need to understand the relationship between vertex cover and independent set. You need to understand the relationship between independent set and clique, and you need to understand the relationship between vertex cover and clique. Basically, any two of these three concepts, between them you need to understand the relationship. So before we solve this question, let's quickly do the recap of all the concepts that are required to solve this question. Let's do a quick recap of relationship between clique and independent set. What is a clique? Clique is set of pairwise adjacent vertices. Set of vertices which are pairwise adjacent means every two vertices are adjacent. So I can say clique is basically a complete subgraph Km. In the graph G, a complete subgraph Km, that is your clique. Okay. So very simple. A set of vertices which are pairwise adjacent. And what is independent set? This is set of vertices which are pairwise non-adjacent. Means every two vertices are non-adjacent. So you can see, for example, if four vertices, let's take four vertices A, B, C, D. Let's take these four vertices A, B, C, D. If A, B, C, D is a clique, okay, this is set of vertices. If this is a clique, then what will happen? If this is set of four vertices, if this is a clique means pairwise adjacent, means every two vertices are adjacent, then in this situation what will happen? Because these are pairwise adjacent, so there is edge between every two of them. Okay, yes or no? So you got a complete subgraph K4. Correct? Now the same situation let's consider for independent set. If ABCD, if this is independent set, if this is a independent set, then what will happen? This set of four vertices, if this is an independent set, then independent set means pairwise non-adjacent vertices. Okay, then in this situation, these are pairwise non-adjacent. Every two vertices are non-adjacent, means there is no edge between any two of them. Yes or no? So this is the situation you will get in the independent set, and this is the situation you will get in the clique. Okay, in the clique you will get this situation, pairwise adjacent, and in the independent set you will get this situation, pairwise non-adjacent. I hope you understood. Now let's see the relationship between clique and independent set. What is the relationship? It's actually very simple. Let's consider graph GVE. What is complement of a graph? We have already seen complement of a graph, that is G complement. It will have the same vertex set. The vertex set will be same, but edges will complement. Means in the G complement we have those edges which are not in G. If there is a edge in G, then that will not be in G complement. If there is no edge between A comma B, between two vertices, if there is no edge in G, then that edge will be in the G complement. So remember, in the G complement we have those edges which are not in G. Very simple. Okay, so now you consider in G, in the graph G, let's assume that S is clique. Okay, let's assume if S is clique. Okay, consider this situation. Let S be a clique. So in the graph G, S is a clique. If S is a clique, what it means? It means every two vertices of S, they are adjacent. Okay, so tell me what will happen in G complement. In the graph G, S is a clique. S is set of vertices. Okay, you already know S is subset of vertices, which are subset of vertices which are pairwise adjacent. Which are pairwise adjacent. This is the definition of clique. So tell me what will happen in the G complement. In the G complement, we have those edges which are not in G. So you can see in the G complement, basically we will do the complement of edges. So here you can see in this S, between every two vertices there is a edge. So in the G complement, these edges will not be there. Means this S will become independent set. Yes or no? This will become independent set. Okay, let's assume S is ABCD. There are four vertices in S, ABCD. Then you can see that in the graph G, this S is clique, means between every two vertices ABCD there is a edge. So these edges will not be there in the G complement, because in the G complement we do the complement of edges. So G complement has those edges which are not in G. So you can see that in G complement, between these vertices there will be no edge, means this S is independent set in G complement. Very simple. Similarly, you can notice, let's assume that S is independent set in G. Let's assume S is independent set in G. If S is independent set in G, then it means that between every two vertices of S there is no edge. Okay, whatever two vertices of S you take, there is no edge, they are non-adjacent. So in G complement we have those edges which are not in G. So between any two vertices of S there is no edge here. So when we do the complement of edges, then in G complement this S will become clique. Okay, yes or no? Because here you can see that between any two vertices there is no edge. So in the G complement, when you do the complement of edges, then between every two vertices there will be edge. Yes or no? So you can see that this is the relationship, that in the graph G, if there is a clique, then that will become independent set in the G complement. In the graph G, if there is independent set, then that will become clique in the G complement. When you complement a graph, then the clique will become independent set and the independent set will become clique. Okay, that's it. Okay, so finally I can say this is the statement, relationship between clique and independent set. If S is a clique in G, then in G complement S will become independent set. If S is independent set in G, then in G complement S will become clique. So you can see S is a clique in G if and only if S is independent set in G complement. So remember these two concepts, clique and independent set, these two concepts, they are complementary in G comma G complement. Okay, I can say when you complement the graph, then the clique will become independent set. When you complement the graph, then independent set will become clique. Okay, very simple. These are some more points you can see. These 2 points we have already seen, that if S is a clique in G, then in G complement S will be independent set. Okay, and similarly if S is independent set in G, then in G complement S will be clique. Let me tell you some more points. When we complement the graph, then maximum clique will become maximum independent set. Maximum independent set will become maximum clique. When we complement the graph, then maximal clique will become maximal independent set. And when we complement the graph, then maximal independent set will become maximal clique. Okay, so you can see if S is maximum clique in G, then S will be maximum independent set in G complement. Similarly, if S is maximal independent set in G, then S will become maximal clique in the G complement. Okay, very simple. I hope you understood. Let me tell you just one more point. Let's assume you have this graph G VE. Okay, and in this graph GVE, let's assume that S is largest clique. Okay, S is maximum clique. S is maximum clique. If S is maximum clique, then what is the size of S? Size of largest clique, that is clique number, and that is denoted by omega, omega of G. Now you already know that in G complement what will happen? In G complement we have same set of vertices but edges will complement. So in the G complement what will happen? If S is clique in G, then S will become independent set in G complement. If S is maximum clique in G, then in G complement what this S will become? This S will become maximum independent set. Maximum independent set. Okay, so you can see in G complement S is maximum independent set. So what is the size of S? Size of maximum independent set, size of largest independent set, that is called independence number, that is denoted by alpha. So I can say alpha of G complement, because here the graph is G complement. So alpha of G complement, that is size of S. So here you can see omega of G is size of S. Here alpha G complement is size of S. So overall I can say, from here I can say that, so I can say that you can see that omega of G, that is same as alpha of G complement. Means the clique number of G is same as independence number of G complement. Okay, I can say the size of largest clique in G, that is same as size of largest independent set in G complement. Similarly, the size of largest independent set in G, that is same as size of largest clique in the G complement. Okay, so you can see, similarly I can also say that alpha of G means the size of largest independent set in G, that is same as size of largest clique in G complement. Okay, so very simple. I hope you understood. You can see, if S is a clique in G, then S will become independent set in G complement, because in the G complement we have those edges which are not in G. We do the complement of edges. So you can see, clique means pairwise adjacent vertices, independent set means pairwise non-adjacent vertices. So when we complement the graph, when we complement the edges, then clique will become independent set will become clique. If S is maximum clique, then when you complement the graph, then maximum clique will become maximum independent set, and maximal clique will become maximal independent set. Okay, very simple. I hope you understood all these points. Now let's see the relationship between clique and vertex cover. Remember, so far we have seen the relationship between clique and independent set. We have also seen in this lecture, we have also seen with proof the relationship between vertex cover and independent set. Now, what is the relationship between clique and vertex cover? Remember, you don't need to remember it. The relationship between clique and vertex cover, you don't need to remember it. You can prove it on the spot. In the exam, on the spot, you can prove it from the previous results that we have seen. So let me tell you here. So far, we have already seen with proof the relationship between vertex cover and independent set. What was the relationship? We have already seen that vertex cover and independent set, these are complementary within the G itself. Means, if a subset of vertices S, if that is vertex cover, then the remaining vertices V minus S will be independent set in the G. So remember these two concepts, vertex cover and independent set, these are complementary within the graph G itself. We have also studied with proof the relationship between independent set and clique. What is that relationship? We have already seen that independent set and clique, these are complementary concepts in G, G complement. When you complement the graph, then independent set will become clique and the clique will become independent set. So these two relationships we have seen, and these are important. Now remember, from these two relationships, we can find the relationship between vertex cover and clique. So see, very simple point. Between vertex cover and independent set, we have relationship. This we have seen. Between independent set and clique, there is a relationship that we have seen. Now between vertex cover and clique, the relationship we can easily find out from the previous relationships that we have seen. So again, I am telling you that relationship between clique and vertex cover, you don't need to remember it. You can prove it on the spot in the exam using the previous results. Okay, now let's see it. So let's see the relationship between clique and vertex cover. This is actually very easy. Let's assume this is the graph G and this is the graph G complement. In the G complement, we have same set of vertices, but edges will complement. Okay, so just tell me some points. In G, let's assume that S is a vertex cover. S is a vertex cover. Okay, S can be any vertex cover. S is some vertex cover. Now we already know that if S is a vertex cover in G, then we already know that the remaining vertices will be independent set in G. Yes or no? So if S is vertex cover in G, then the relationship between vertex cover and independent set, that we already know. Okay, so this implies what? This implies that the remaining vertices V minus S, this is an independent set. Do you agree? So far, do you agree that in the graph G, if S is a vertex cover, then we already know the relationship between vertex cover and independent set, that if S is vertex cover, this set of vertices, this subset of vertices, if this is vertex cover, then the remaining vertices V minus S will be independent set. Now, we also know that if V minus S is independent set in the graph G, then this V minus S will become clique in the G complement. we already know the relationship between independent set and clique. So remember, from here, what it implies, it implies that this V minus S, this is a clique, in G complement. Yes or no? Is this clear? So did you notice? Finally, I can say that if S is vertex cover in G, then V minus S will be clique in the G complement. Okay, so you can see from here we imply this, then from here we imply this. Okay, I can simply say that, okay, overall I can simply say that from here we can imply this. So this is the conclusion. So will you remember it? Tell me, this conclusion, will you remember? No, don't remember, because you just remember the relationship between vertex cover and independent set. You already understand the relationship between independent set and clique. So from these two, you can easily find the relationship between vertex cover and clique. So we have already seen that if S is a vertex cover, then V minus S will be clique in the G complement. In the graph G, if S is vertex cover, then in the G complement, V minus S will be a clique. Okay, and this is the whole proof. Very simple. I hope you understood. Let's see one more thing. In the G, let's assume S is a clique. Okay, S is a clique. In the G, let's assume S is a clique. Now, we know if S is a clique in G, then the relationship between clique and independent set we already know. Okay, so what this implies? If S is a clique in G, then in the G complement, this S will become independent set. Yes or no? So S has become independent set. S will be independent set in G complement. Now remember, we already know the relationship between independent set and vertex cover. If S is independent set in G complement, what it implies? It implies that the remaining vertices V minus S, this is a vertex cover in G complement. This is a vertex cover in G complement. Okay, so overall what we got that if S is a clique in G, then V minus S is a vertex cover in G complement. Okay, in G complement. So overall I can say that basically this is what we got. This is the conclusion we got. Tell me, will you remember this conclusion? The relationship between clique and vertex cover, will you remember? The answer is no, because you just understand the relationship between clique and independent set and the relationship between independent set and vertex cover. Then you can easily prove the relationship between clique and vertex cover. Okay, so that's it. This is the relationship between vertex cover and clique. You can see if S is a vertex cover in G, in the graph G, if S is vertex cover, then in G complement V minus S will be clique. In graph G, if S is clique, then in G complement V minus S will be a vertex cover. So I can say that S is a vertex cover in G if and only if in G complement V minus S is a clique. Or we can say the same statement, we can say that in G, S is a clique if and only if in G complement V minus S is a vertex cover. Again, I'm saying there is no need to remember it. You don't need to remember the relationship between vertex cover and clique. You can prove it on the spot. In the exam, on the spot, you can prove it using the previous results. Okay? I hope you understood. Everything is clear. Just one small point I'm telling you, just for sake of completion, let me tell you this point. Again, you don't need to remember it, but let me tell you this point. In the exam, on the spot, you can prove it. So what we have seen that if S is vertex cover in G, then in G complement V minus S will be a clique. Okay, this is if and only if, means the vertex cover, if there is a vertex cover if S is a vertex cover in G, then in G complement the remaining vertices V minus S will become a clique. Similarly, if S is a clique in G, then the remaining vertices V minus S will become a vertex cover in the G complement. Okay, so this is what we have seen. This you already understood. Now you can see that this is the G VE. Okay, and this is G complement VE complement. Now in this G, let's assume that in G, let's assume that S is a minimum vertex cover. If S is a minimum vertex cover in G, then we have already seen that in G complement, this V minus S, this will become what? This will become maximum clique. Okay. So very simple. We have already seen that if S is vertex cover in G, then in G complement, V minus S will become a clique. Similarly, here I can say that if S is a minimum vertex cover in G, then in G complement, V minus S will become maximum clique. Okay. Now, you know that if S is minimum vertex cover, then what is the size of S? Size of minimum vertex cover, size of smallest vertex cover, that is called independence number, that is called beta, beta of G. And you can see size of maximum clique in G complement. What is that size of maximum clique? That is called clique number, that is denoted by omega. So omega of G complement, that is equal to size of V minus S. What is size of V minus S? That is size of V minus size of S, that is N minus size of S. So from here what you can see that, so I can say that omega of G complement means clique number of G complement, that is equal to N minus size of S. Size of S is beta of G. Size of S is same as beta of G. So from here what we got? We got that beta of G plus omega of G complement, that is equal to number of vertices. Okay, don't worry, you don't need to remember it. I'm just telling you that you can prove it on the spot. Okay, all these results. So you can see that beta of G plus omega of G complement is equal to number of vertices. The same thing you can also say that omega of G plus beta of G complement, omega of G plus beta of G complement, that is equal to number of vertices. That is also fine. Okay, so of course there is no need to remember all these formula, all these things, all these statements. You don't need to remember. You can prove it on the spot in the exam using the previous results. That is the reason we have seen the proof. I hope you understood. So far everything is clear, let me know. Now let's solve this TIFR CS 2024 question. Every concept that is needed to solve this question, we have already seen. We have done the recap of all the concepts required to solve this question. We have seen the proof, everything. Okay. Now you can easily solve this question very easily. So the question is saying for an undirected graph G, G complement is the complement of the graph. And this definition is given to you that complement of a graph, that is basically that has the same vertex set. The vertex set will be same, and you can see G complement has those edges which are not in G. Okay, so there is a edge in G complement if and only if this edge is not present in G. So basically the definition of complement of a graph is given to you. Then consider the following statements. 5 statements are given to you, and the question is asking which of the following is true for any graph G and its complement G complement. So you can see any graph G and its complement graph G complement, which statements are true. Okay, and what are the options? 1 is equivalent to 3,4, 1 is equivalent to 3,5, 1 is equivalent to 2,4, 1 is equivalent to 2,5. None of these statements are equivalent to each other. What are these statements? These are saying G has vertex cover of size at most k, G complement has independent set of size at least k, G has independent set of size at least n minus k, G has clique of size at least k, G complement has clique of size at least n minus k. So this question, it is looking like complicated question, but let me tell you, this is actually extremely easy question. All the concepts required to solve this question we have already seen. So let's solve this question now quickly. So let's focus on the first statement, because you can see in the options, the question is asking that first statement is equivalent to whom. Okay, in all the options, in every option, they are asking that the first statement is equivalent to which other statements. Okay, so let's see what this first statement is saying. First statement is saying that G has a vertex cover of size at most k. G has a vertex cover of size at most k. Okay, now let's see this statement is equivalent to which statements. Okay, so let's find out. Let's not worry about this question, forget about this question now. Okay, let's focus on this statement now. So the graph G has a vertex cover of size at most k. We already know the relationship between vertex cover and independent set. Okay, what is that relationship? This relationship, if you remember, between vertex cover and independent set, let's assume this is the graph G. This is your graph GVE. Okay, and in this graph GVE, there is a vertex cover of size at most k. Let's assume that vertex cover, let's call it vertex cover S. Okay, for a moment I'm calling it S. There is a vertex cover, let's call it S. Okay, so this S is vertex cover. So what about the remaining vertices V minus S? Remember, this subset of vertices S, this is vertex cover, and the question is saying that the size of S, that is at most k, less than equal to k. So tell me, if this S is vertex cover, this is a vertex cover. The question is saying that this is a vertex cover. If this is a vertex cover, then what about the remaining vertices? We have already seen the relationship between vertex cover and independent set. So we have already seen that in any graph, if S is a vertex cover, this subset of vertices S, if this is a vertex cover, then the remaining vertices, they will make independent set. So you can see V minus S, this will be an independent set. Okay, very easy. Now you tell me a very simple point. If the size of S, the size of this area, if that is at most k, then what can you say about the size of V minus S? Tell me, what can you say about the size of V minus S? So this is a very easy point, that if this S, this is a vertex cover which has size less than equal to k. So if this area has less than equal to k vertices, then in the remaining area, how many vertices will be there? That will be greater than equal to n minus k. Yes or no? Okay, so you can see the size of this S, this is less than equal to k. Then what about the size of V minus S, these remaining vertices? So that will be greater than equal to n minus k. If you did not understand, don't worry, you can do it mathematically. So the mathematically it will be like this. You can see size of S is less than equal to k. What about size of V minus S? Size of V minus S, that will be equal to size of V minus size of S. Size of V, let's assume that is n, size of V. So I can say size of V minus S, that will be equal to n minus size of S. We already have size of S less than equal to k. If I multiply this inequality by minus on both sides, then this direction of this inequality will change. Yes or no? This inequality will change. So you can see minus size of S is greater than equal to minus k. If I add n on both sides I am adding this n. So finally n minus size of S, that is greater than equal to n minus k. So mathematically also you can see, actually very intuitively also you can see, this is very common sense, or I can say very logical, very intuitive, that these vertices, I can say the number of vertices in this area S, if that is less than equal to k, then how many remaining vertices will be there? That will be greater than equal to n minus k. Okay, and we have already seen that if S is vertex cover, then the remaining vertices will make independent set. So one thing you can notice here, that if the graph G has a vertex cover of size at most k, then graph G has an independent set of size at least n minus k. Is this clear to everyone? Very simple point. What we are saying that if G has a vertex cover of size at most k, then we have already proven that in this situation G has an independent set of size G has an independent set of size greater than equal to n minus k. Okay, and remember this is both ways means if the graph G has an independent set of size greater than equal to n minus k, then the graph will have vertex cover of size at most k. Okay, this direction also we can prove. So let's see this direction also. Basically, consider this statement. Consider this third statement that G has an independent set of size at least n minus k. Okay, so consider this third statement. The third statement is saying that G has an independent set of size at least n minus k. This is what third statement is saying. Now, if G has an independent set of size at least n minus k, then what about the vertex cover? See, very simple. We already know the relationship between independent set and vertex cover. So this is your graph GV comma E, where the number of vertices that is equal to n. Okay, and here we have independent set. There is an independent set of size at least n minus k. Let's assume that independent set. Let's assume that is P. Okay, independent set is P. So you can see we have P. This is subset of vertices, and this P is an independent set. This is an independent set, and the size of P that is greater than equal to n minus k. So what about the remaining vertices? Remaining vertices means V minus P. What about these remaining vertices? We already know that if this P, this subset of vertices, if this is independent set, then the remaining vertices that will be vertex cover. Yes or no? So this is a vertex cover. Now, can you tell me the size of this vertex cover? You can see size of P is greater than equal to n minus k. So what can I say about the size of V minus P? Size of V minus P, that will be less than equal to k. Okay, you can mathematically also prove it, but intuitively also you can see the total number of vertices is n. So in this area, if we have at least n minus k vertices, then in the remaining area we have at most k vertices. If you want to prove mathematically, that also you can do. You can see that the size of P is greater than equal to n minus k. Okay, so what can I say about the size of V minus P? This will be equal to size of V minus size of P. Size of V is n. Okay, so you can see here size of what I can do, I can take k on this side. I can take k on this side, and I can take size of P on this side. Okay, so you can see that size of V minus P, this is size of V minus P. Yes or no? This is size of V minus P, and this is less than equal to K. Okay, so finally what we got? We got size of V minus P less than equal to K. Is this clear? So this is the same thing I'm writing here, that size of V minus P is less than equal to K. So what is the conclusion now? The conclusion is this, that this third statement implies the first statement, the first statement implies the third statement. Okay, this is the conclusion. Notice one thing. You can see this is the third statement. Okay, third statement implies first statement implies third statement. So I can say that first statement is equivalent to third statement. Is this clear? Very simple. It's nothing complicated. It's actually very simple. Did you understand? Please tell me. We have proven that if the graph G has a vertex cover, any vertex cover of size at most k, then graph G has an independent set of size at least n minus k. And the other direction also we have proven that if the graph G has an independent set of size at least n minus k, then the graph G will have vertex cover of size at most k. So you can see the first statement implies third statement implies first statement. The proof we have seen, proven. We have already proven it. Very simple. I hope you understood. So I can say that first statement is definitely equivalent to third statement. Okay. What else? What else we can say? So let me tell you. You can see now, just focus on the third statement again. Third statement. Third statement is saying that G has an independent set. G has an independent set. Let's call it P. G has an independent set P of size at least n minus k. Okay. Now we already know the relationship between independent set and clique. What is that relationship? Do you recall? So you can see in the graph G, if P is an independent set, then in the G complement, this P will become clique. Yes or no? Okay, very simple point. This you already know that in the graph G, G V comma E, and this is G complement, V E, E complement. Okay, so you already know that in this G, if let P be a independent set, okay, then in G complement, what this P will become? Then in G complement, this P will become clique. Okay, yes or no? This will become a clique. So you can see this will become a clique. So here you can see if this P has size greater than equal to n minus k, then the same P will become a clique when you complement the graph. In the G complement, this P will become a clique. So of course here also P size is greater than equal to n minus k. So we can say that if G has some independent set P of size at least n minus k, then G complement has a clique of size at least n minus k. Yes or no? And remember, the same thing is two ways. Okay, yes or no? You can see in G complement, if there is a clique of size at least n minus k, then when you complement the graph, then this clique will become independent set. Okay, yes or no? So this is again two ways. Yes or no? Now you read the fifth statement. Read the fifth statement. This is saying G complement has a clique of size at least n minus k. This is the fifth statement. So you can see basically the fifth statement. This is the fifth statement. The statement fifth implies statement third, and statement third implies statement fifth. Okay, is this clear? Statement third implies statement fifth implies statement third. So I can say that statement third is equivalent to statement fifth. Is this clear? Very simple. See, very easy. What was the fifth statement? The fifth statement is saying that G complement has a clique of size greater than equal to n minus k. Okay. So the point is very simple, that if G has an independent set P of size at least n minus k, then when you complement the graph, then independent set will become clique, and when you complement the graph, then clique will become independent set. Yes or no? The same P, the same set P, if it is independent set in G, then it will become clique in the G complement. The same set P, if it is clique in the G complement, then it will become independent set in G. Okay, so you can see that this third statement, this is equivalent to fifth statement. Okay, this is the one thing. Also we have also seen that first statement is equivalent to third statement. So remember, first statement is equivalent to third statement is equivalent to fifth statement. So overall I can say that first statement equivalent to third statement equivalent to fifth statement. Okay, so what is the correct answer? You can see first statement is equivalent to third comma fifth. Yes, option B will be the correct answer. I hope you understood. It's actually very easy. This question is not complicated. Basically, this question is based on the relationship among these concepts: vertex cover, independent set, and clique. Okay, and remember the relationship between vertex cover and independent set. What is that? In the same graph G, if S is a vertex cover, then the remaining vertices will be independent set. In the same graph G, if S is an independent set, then the remaining vertices will be vertex cover. This is the relationship between vertex cover and independent set. And what about the relationship between independent set and clique? This is G complement. in G, if S is a independent set, then in G complement S will become clique. Okay, similarly, in G, if S is a clique, then in G complement S will become independent set. Okay, so when we complement the graph, then independent set will become clique and clique will become independent set. So this is the relationship between clique and independent set, and this is the relationship between vertex cover and independent set. So very easily, using these two concepts, using these two relationships, we can easily see that the statement 1 is equivalent to statement third is equivalent to statement fifth. Yes or no? Because if the graph G has vertex cover of size at most k, then the remaining vertices will make independent set. So in the graph G, the remaining vertices will make independent set. So if vertex cover has size at most k, then how many remaining vertices are there? That will be at least n minus k. So you can see G has an independent set of size at least n minus k. Okay, similarly, notice one thing, that there is a relationship between independent set and clique. So in G, if there is an independent set of size at least n minus k, then when you complement the graph, then in G complement, this same set will become clique. So in G complement, we have a clique of size at least n minus k. Okay, yes or no? So finally, I can say that first, third, and fifth, they are equivalent. What about second comma fourth? Look at the second. Let's see the second statement. Let's see the second and fourth statement. Are they equivalent? The second statement is saying G complement has independent set of size at least k. Okay. So the second statement is saying G complement has an independent set. Let's call it P. Okay, let's call it P. So G complement has an independent set, or anything you can call it. Okay, you can call it Y. So G complement has an independent set Y of size at least k. Of size at least k. This is the third statement. What is the this is the second statement. This is the second statement. What is the fourth statement? G has a clique of size at least k. G has a clique of size at least k. Now, again, you notice we already know the relationship between clique and independent set. So in G, if there is a clique of size at least k, okay, see, let's assume that there is a clique, and that clique, let's assume that is Z. Okay, let's assume. So there is a clique Z of size at least k. Now you already know that this fourth will imply second. This fourth statement will imply second statement. Why? What is the reason? Because in G, if there is a clique Z of size at least k, then definitely when you complement the graph, then this clique will become independent set. Yes or no? When I complement the graph, then this clique will become independent set. So I can say in the graph G, if there is a clique of size at least k, then when you complement the graph, then this clique will become independent set. So I can say that in the G complement, there is an independent set of size at least k. So I can say that fourth statement definitely implies second statement. What about second statement implying the fourth statement? Can I say second statement will imply the fourth statement? Yes, second statement will imply the fourth statement. How? Because in G complement, if there is an independent set of size at least k, when you complement the graph, then independent set will become the clique. When you complement the graph, then you can see in the G, this independent set Y will become the clique. So if G complement has independent set of size at least k, then when you complement the graph, then in G, this independent set will become the clique. So yes, in the G, there is a clique of size at least k. So second statement implies fourth statement, and fourth statement implies second statement. So what I can say overall? So I can say that second statement is equivalent to fourth statement. Okay, so remember, second statement is equivalent to fourth statement. This is also correct, that second statement is equivalent to fourth statement. But the question is asking that this first statement is equivalent to whom? So this first statement is equivalent to third comma fifth. But this is the complete analysis, that second statement is equivalent to fourth, and first, third, and fifth, they are equivalent to each other. Okay, I hope you understood. This is the complete analysis of this question. Is this clear? Let me know. So this is enough for this session. In this session, we have done some questions from GATE PYQs, TIFR PYQs with complete analysis, with revision, with recap, all the questions we have done with complete analysis. So I hope you loved this session. I hope you enjoyed this session, and I hope you understood everything that we have seen in this session. Okay, in the next session, we will continue. We will solve the remaining TIFR PYQs and GATE PYQs. Okay. Thank you, everyone. Please share your feedback. Please let me know in the comments. Did you enjoy this session? Did you understand everything in this session? Okay, let me know. Okay, thank you.